All right, good evening, ladies and gentlemen. It is section 4.8, which is differentials. I think you're gonna like this. This is kind of cool. We're gonna do something called linear approximation to start off with. And here's the idea. I'm gonna draw this graph x squared, and I'm gonna draw it a little bit more obnoxiously in the sense that I wanna put a little bit of curve to it, okay? And there's this tangent line that will touch right there at 2. And so I'm going to draw 2 units here. And vertically, I have to go up 4. Now, it's supposed to touch up here at 4. I'm just going to draw these tick marks up to that spot. Okay. Now, I know that my bandwidths aren't as big vertically as they are horizontally, but that's okay. I'm just trying to emphasize a point here. And the idea is this, is that I can fill in these values probably using a calculator pretty easy. So I know 2 squared is 4. I know 1.9, which is a little bit further away on the left-hand side of 2, gives me 3.61. And 1.99 is closer to 2, which means it'll probably give me an answer closer to 4. It does 3.9601. All right. And from the right side, 2.1 squared. Sometimes I can do that like on a little scratch paper, or maybe, I know 21 squared maybe is 441. Maybe do that in our head. And then 2.01, I can't square that in my head too easily, but that is 4.0401 if I were to actually work that out, okay? Now here's the idea, is that sometimes values like this and this, and maybe even the ones on the end here, on each side, they're kind of too hard to do in your head. And unless you had a calculator that had a squaring feature on it, they may not be possible to do, okay? However, with some simple multiplication, a little bit of addition or subtraction, you can find something very, very close to the square root of, the square of 2.01, just using some simple procedures that we typically do in a linear fashion, okay? And here's the idea, is that this line here, well, it doesn't quite look like this, but there's an area where they kind of share points that are pretty close together, okay? And maybe the area is about somewhere between the 1 and, I don't know, maybe 2.5. It looks like the distance between the curve and the tangent line it's actually very small, okay? And so here's what I'm going to do. I'm going to make the equation of a tangent line, and that's going to be this guy right here, the one I'm just going to star. And I'm going to say that's y minus y1 equals m times x minus x1. And if I have agreed to mark it at the point of tangency located in this question, which was 2, 4, at right there, and that seems to be where we surround our values in our table at x equals 2, then I can plug in 2 for x and 4 for y. Okay. And so this equation of this line is actually pretty close to this curve with a really, really tight domain, okay? Especially between 1.9 and 2.1. If I draw that in, 1.9 is gonna be right here, 2.1 is right there. These points between the curve, let's say the distances between the curve and the respective tangent line, those distances are pretty small. They're almost zero, okay? Nevertheless, here's what I'm gonna do. I gotta find m, okay? M is the slope of this tangent line, and how do I find it? Well, if f of x is x squared, then f prime of x is 2x, and f prime of the x value that I'm looking for, which is 2, is 2 times 2, which is 4. So y minus 4 is equal to 4 times x minus 2. Okay, now traditionally I tell you just leave it, okay? Let it just stop right there. But I actually want to solve for y here, okay? So let me do this. Let me put the 4x minus 8 there. And then if I add 4 to both sides, that is 4x, I think, minus 4. Okay. All right, now why is that important? Well, they call this t of x, that's what this is. And they call it t of x is because this is the function that's the tangent line that is tangent to this parabola at the given point they asked for, which is 2, 4. Okay, and what am I going to do? Well, I'm going to plug in each of these 5 values in for x. So 4 times 2 is 8, minus 4 is 4. So that gave me actually the same thing as it should, because the parabola of x squared and the tangent line share this point 2, 4. That's how we created this equation. Okay. However, if I want to work on this a little bit more, I could do 2.01. And so let me test that. I'll just write this off to the side. F of 2.01 equals 4 times 2.01 minus 4. And if you do this math, this becomes 8.04 minus 4. Okay, and that turns out to be 4.04. Now, is that exactly the same? It's not, but you can see, darn it, that it's pretty close. Tens, hundred thousands, 10,000s. The gap between these two is 1 over 10,000. Okay, so while we're using a line to approximate, yeah, that gap between this parabola and that line is so small. Okay, so small. I could do the same thing with 2.1. Okay, it's a little bit further away, and when it becomes more further away, the gap will get a little bit bigger. That should not surprise us, but let's just plug it in. F of 2.1 is 4 times 2.1 minus 4. And so this becomes 8.4 minus 4, which is 4.4. All right, and what is that gap? The gap is 0.01. All right, so it's still a hundredth of a, it's 1/100th away in terms of a distance, but dang, that's a pretty good approximation considering this is just a line that's supposed to help represent what this parabola is at some tight locations. Okay, so yeah, this is good. If I do f of 1.99, okay, so that becomes 4 times 1.99 minus 4. That gives me, I think, 3 points. 7 point something. Let me try that. 4 times 1.99. So, sorry. It's late. But here we go. 7.96 minus 4. And what does that give me? That gives me 3.96. Okay, and again, are these far off? It's the same as what we had before. It's 1 over 10,000 in terms of a gap. So there's not much error between what's actually correct versus what this approximation is. Okay, and again, this approximation is just a line. It's a very simple, fundamental representation of a function that approximate this figure quite nicely. Okay, that parabola. So the last one is for this last value of 1.9. All right, and send 4 times 1.9 minus 4. 7.6 minus 4 is positive 3.6. And still, we're still 1/100th away. Okay, so so this is what linear approximation is. Okay, they'll give you some value. Okay, in this case, it's 2, 4. And you'll make an equation of a line that is tangent at that specific value. In this case, it was 2, 4. You'll have to take the derivative of your function. This was a nice one. It was just 2x. Okay, we did that part right here. And then you have to input the x value that they give you in order to find the equation of the, it's not the equation, the slope of the tangent line. In this case, it was just 4. All right. And then once you solve for y, which I have right here at the very bottom, I'll box it again. All right, it's really easy to plug in these x values that in turn will give you approximations of y, or I'll say f of x, approximations for that f of x in the representation of t of x. Okay, so that the t of x is actually the true estimate. Okay, but you'll notice that that estimate is very close to what should be the f of x value. Okay, and again, some people say, why don't you just plug it into here? That was just so easy to do. The idea is that sometimes you have these elaborate functions, okay, that aren't easy to manipulate as you input these values, okay, kind of mentally, okay. Otherwise, you could do these on the side with these approximations, with this line here, this linear approximation. You could do these more easily in your head, okay. You don't need fancy calculators that have squared buttons or square roots or signs, etc. to work them out. You can just use a linear approximation, and it gives you something pretty dang close, okay. All right, here's the next piece. Sorry if I'm getting stuff that shows up here. I'm gonna move things. Okay, so let's find the differential dy, okay? And you've done these before. Here's the idea. All you have to do is take the derivative of each side. So with respect to the left side, you have to take the derivative with respect to y, which is dy. And you're like, well, should I take the derivative of x too? Yes, do that on this side. And you're just gonna do a power rule. So 3 times, I put a 1 underneath it to make this easier, 2/5 x to the, and then subtract 1 to this, -3/5. Okay, 2/5 minus 1 is -3/5. That will give you 6/5 x to the -3/5, and that's 6/5 x to the 3/5. Okay, my dy will stay there. My differential will stay on this right side. And that is as far as you need to go. All right, next one over here, same idea. Let's take a dy. Okay, and then this will involve a chain rule and a product rule. Okay, so I'm going to write it in a way that's a little bit better, but this will be first times the derivative of the second. Now when I take the derivative of the second half, that's 1/2, 1 minus x squared to the -1/2 times the derivative of the inside, which is -2x. Okay. And so what happens here, the 1/2 and the -2 will go away, and my x will stay on top, and this piece here will go on the bottom. 1 minus x squared, the positive 1/2. Your dy will stay here. I'm sorry, you'll take the differential to the right here, derivative with respect to x to the right, and we are done. Okay, I don't know if this is mathematically correct, but we'll just say that these are kind of like the variable that you're taking the derivative with respect of. So if we're taking different derivatives with respect to x, we're gonna kind of address it on this back piece right here. Okay, just create some information for our reader in terms of what we're doing. Okay. Okay, I'm going to skip that next one that may be in your notes. I'm just going to go to the last one. And here's the idea. It says estimate the square root of 9.1. Now, I'm going to cheat for a second. Actually, you know what? I'm not going to cheat yet. I'm not going to use my graphing calculator. And here's the idea. It's like, can I figure this out without using my graphing calculator? Can you take the square root of 9.1 in your head? Okay. Now, I know what comes to mind. You're like, well, I don't know 9.1. But I do know this, that if I were to change this and put it into some type of equation, or maybe even a function, that the square root function resembles that, okay? And if I take a look, the square root function may look something of that nature, okay? And the idea is that you know that the square root of 9, if I let x equal a number kind of close to this, that's kind of easy to work with, 9, and I input it in for that square root bar, square root of 9 is 3. All right, so 1, 2, 3, 4, 5, 6, 7, 8, 9, up 3. There you go. All right, now I don't know what that is in my head. Okay, I know something close to 3. Okay, this is something close. And the idea is I'm going to do the same thing that I did before. I'm going to create a tangent line at that spot. And it's going to be you'll see it's pretty close to my my curve, right? And I would say that there are many points, maybe anything from between here and here, have values that are almost landing on top of it, but not quite. Okay. But nevertheless, I'm going to treat this the same way. And probably the hardest part is just figuring out what function you're going to use. And since this is a square root function, I'm just going to write the square root of x. And I'm going to pick something close to 9.1 that I know square roots nicely, and that is just 9, and I know it gives me the answer of 3. Okay, so once you know that, you're in pretty good shape. So y minus y1 equals m times x minus x1. And I know what x and y are. Y is 3, and x is 9. Okay, and so how do I find m? Same way as you did the first problem. You're going to take the derivative here. This gives me, I'm getting in a pretty good habit of knowing that the square root of x derivative is just 1 over 2 square root of x. And if I then input the value x of 9, that gives me 3. So that gives me a 6. Okay, and here's the idea. I may not know exactly what 9.1 is, but geez, maybe 9.1 is just to the right of this. And the gap between that and my true green function and the, that's weird to say, but the f of x green function and the red linear tangent line at that point, they're so close together. Okay, so here's the deal. I'm going to solve for y after I plug in the value of x that I'm seeking. Okay, so the x that I want is actually this guy. Okay, so that's going to go into here. The x that you had in the back here, that x1 and that y1, that's the respective point that's close to this after you input it into that function. So I'll plug in 9.1, and I'll add 3. So 1/6. This is 0.1. Now, I can write 0.1, or I could write a 10th. That's the same thing. All right, so 9.1 minus 9 is 0.1, or 1/10. And a 6 times a 10th, I'm going to put this off to the side. A 6 times a 10th is a 60th. Okay, now some of you are like, I don't want to do fractions, and I get it. Okay, like, can I do my fractions on my calculator? No, because here's the deal. The reason why we're doing this is because we're trying to show you a way of finding the square root of 9.1 without using a calculator. And if I have you do fractions on a calculator, then I would just say, you know what? Do the square root of 9.1 on your calculator, which is the wimpy way, okay? And what does this mean? Well, this is just 3 and 1/60th, okay? And that should be pretty close to the square root of 9.1, okay? So just to show that we are pretty darn close, what I'd like you to do now, just to verify our work, again, this is the approximation. Okay, at x equals 9.1 for the linear regression, not the linear regression, the tangent line. Teach statistics too. Okay, for the tangent line. And so I'm just going to take 1 divided by 60. Okay, and that gives me about, if I do my calculus AP way, 3.0167. Okay, darn it. And if I do the square root of 9.1, okay, which is just to verify, the square root of 9.1 gives you also 3.01662. Okay, and so this, you can see they're so close. Okay, you have to go 1, 2, 3, 4, 5. Okay, 5 place values to the right before you actually have a change. Okay, now here's what they sometimes say. And while if we were to do this on an AP test, we always go to 3 place values to the right, 3 place values to the right. Those are identical in terms of answers. Okay, even though we know deep down one's a little bit bigger. Sometimes they'll say, is your prediction an underestimate okay, or an overestimate. Okay, and I know you can look at this and say, oh, well, our prediction here was an overestimate. It's a little bit higher than what really was supposed to happen. And that's true, okay, and I know you get that you can look at the numbers and say, hey, this one's bigger. This was our prediction because of our tangent line. This is our true function, and this one has a higher y value than this one, okay, or an output value. But here's the deal. If you look at this curve, okay, and I'm going to exaggerate just a little bit more, and this is my tangent line, which I'm trying to draw straight, okay? Anytime your curve, okay, your function, okay, is concave down, okay? If it's concave down, okay, then your tangent line will be an overestimate. Okay, and it's just because all these points that you're using here to predict an output for these guys, okay, they're all higher, okay, because it's concave down. If it was the reverse and it was concave up, okay, then your tangent line would be on the bottom and all of your values underneath would be underestimates. Okay, and they may be super close to what you have here, but again, they're close, but they're underneath. Okay, it's an underestimate if you are concave down. Okay, and they'll ask you that. Sometimes they'll say, hey, is this estimate that you found here an underestimate or an overestimate? And it's not that they want you to plug things into the original. They want you to know what the curve looks like. Okay, and if you're not sure if something is concave up or concave down, how do we do that? Well, we take a second derivative. Okay. And once you put it in your second derivative and you input values, you can see if they're positive or negative to see if they're concave up or concave down. Okay. So there you go. Okay. Hey, that's it for quarter one. Thank you for your attention. And if you have any questions, you let me know. That is all.